Good afternoon, everyone. Thank you so much for taking time out of your busy schedule to join us for this very special presentation, a professional development webinar on operational design of experiments. Our presenter today is Mark Kimmerly from Air Academy Associates.
Thanks so much, James, for the introduction and the opportunity to be with you today. And I want to thank each of the folks who are out there listening in, and hopefully this session will give you a nice little overview of design of experiments. I'm calling this operational design of experiments because the purpose of my presentation is to show you how to make DOE operational within an organization. Not only to give you the definitions and so forth, but operational DOE means making it operational and exclusively internal to an organization. How do you get the biggest bang for the buck? Our agenda today, we'll cover 6 points. First of all, we're going to go over the terminology of combinatorial test and DOE. We'll look at various approaches to testing multiple factors. Another name for DOE out there in the marketplace is multivariate testing. So with the advent of Six Sigma and design for Six Sigma, that term MVT, multivariate testing, has kind of gone away, and design of experiments has kind of taken over. But we want to talk about multiple testing, multiple factor testing. We want you to take away from today, one of the big questions is, why is DOE different? What makes it so special from other testing techniques? That's a critical and key takeaway for each of you today. We're going to show you how to use DOE to screen multiple factors. Screening means separating the vital few from the trivial many. Using DOE to model or build transfer functions, including interaction effects and so forth. We'll use high throughput testing. I want to show you that technique for confirmation and using it on mixed factor, mixed level testing. And some of these terms may not be familiar to you right now, but as we go through, we'll home in on the definitions and show you what it's all about. As far as the terminology, I like to use a very simple graphical construct like the IPO diagram shown here, input, process, output, because it gives us a good graphical background on which we look at DOEs, because DOE is the best technique to use whenever you want to look at relationships between outputs and inputs of a process. And a testing process is a blending of inputs to achieve some desired output. So the outputs and the inputs, anytime you want to find relationships between the two, DOE is the method of choice. And we're going to show you why it's the method of choice as we go forward. I don't know why this keeps coming up all the time, and I'm sorry about that. But let's go and take an example. Here's a web-based test scenario, performance tuning example, where we have 6 different inputs and 2 different outputs. The outputs are performance measures. In this case, the 2 that we're measuring are the number of home page loads per second. Bigger, of course, is better there. Cost, smaller is better there. And then we have the 6 input variables, or factors as they're sometimes called, in this scenario. So this is a very simple scenario, 2 outputs, 6 inputs, and let's talk about the terminology in DOE or combinatorial test. By the way, every test is a combinatorial test, but only some of them are DOEs. And so the terminology is similar for any combinatorial test, but DOE is a special case of combinatorial testing that we're going to look at specifically today. Y's and X's have different names. Y's, they go by outputs, response variable. You might hear that term for a Y. Critical to customer in the Six Sigma DFSS realm. Critical to customer is a very important term, but it's a dependent variable. And we learned this in school a long time ago. Y values are dependent variables. X variables are independent variables. These are the entities that we are purposely and systematically going to change during a DOE or an experiment. They are also, the X's are also known as inputs or factors, and many times we call them factors. Okay, let me go back to this particular screen here. I apologize for that message continually coming up. And at any rate, we have the X's and the Y's, and we have levels. Now, level is a term that's used for a setting or a unique value for a particular factor, like the factor is altitude. If the one factor is altitude, two different levels might be 500 feet or 5,000 feet. So a level is a unique value or setting of a factor. A run is an experimental combination of the different levels of the different factors. It's a test case. Another name for a run is an experimental test case. A replication is doing or repeating a test case or an experimental combination once or more than once. So when we replicate a design, we typically do the testing of the different test combinations more than once. And for the reason for that is to get a look at variability. An effect is the difference or impact that a factor X has on Y when we purposely change it. We purposely change X to see what effect it has on Y. An interaction effect is a combination effect. That's when the effect of one factor depends on the level of another factor. And time temperature is a very common interaction effect out there because the effect of temperature depends on the time, and time pressure is also, and temperature pressure is also a very common interaction effect that we see in the marketplace today. So those are some of the terms. Now getting back to our performance tuning terminology, the factors would be that we listed in the IPO diagram earlier: the CPU type, the CPU speed, the RAM amount, hard drive size, virtual memory, operating system, and the levels or choices there that you see that I have written down are two different levels for each of the 6 factors. CPU type is clearly a qualitative factor. We either have an Itanium or a Xeon type of CPU. The next 3 factors are all quantitative. You can see that we have 1 gigahertz to 2.5 gigahertz for CPU speed. RAM amount is also quantitative. Hard drive size, quantitative, measured in the number of gigabytes. Virtual memory now and OS are qualitative. Again, OS being a Windows or a Linux type operating system. But I want you to notice that if we were to do a test on these 6 factors, this would be called a 2-level design because we are only testing the factors at 2 levels. In fact, all of them are tested at 2 levels. When we get into mixed factor designs, we have mixed factors here. Some are qualitative and some are quantitative, but they're all at 2 levels. That will not always be the case, especially in the verification, validation, and operational testing. So you see the Y's, you see the X's, and DOE is going to help us answer questions like which factors are the most important. In other words, which factors affect our performance, which do not, and which combination of factor choices will maximize performance. Also, which combination will create havoc with our performance and deteriorate the performance. How do you know for sure? How can you answer those questions? Well, DOE will provide you the data and the analysis and the subsequent analysis and evaluation to help you answer questions like this. Here's another example of a quick IPO. I'll address this one later. You'll see in this IPO the Sonar system test process here. We have target detection range being the primary output or response variable, and then we have 7 inputs. And I'm not going to go through all of these, but you can see them on your screen: submarine depth, power, pulse frequency, and so forth. But I want you to notice that the first factor is at 2 levels. That is, there are 2 choices, shallow and deep, and the other 7 all have 3 levels. So the design we would use in the previous performance tuning example would not be the same design we would use for this one that has 7 factors, 6 of which, it has 8 factors, 7 of which have 3 levels, and 1 of which has 2 levels. So there's 8 input arrows there. We would not use the same design to test this scenario as we would on the performance tuning. Let me quickly go over some approaches to testing multiple factors that you may be familiar with in the past. I do this to be able to compare and contrast DOEs with these different types of techniques. The first one I want to talk about is one factor at a time testing, also known as OFAT. Then I'll look at the subject matter expert or Oracle approach, sometimes known as the best guess approach. All possible combinations, or full factorials as we sometimes call them, are a very good approach. The problem is cost of the test scenario. It means that we'll probably have lots and lots of test combinations, which are prohibitive in most cases, in many cases anyway. The more modern approach is a statistically designed experiment called DOE. which includes full factorials. Full factorials are legitimate DOEs. The problem with them is the cost, as I said before. And there are other selected designs that are out there in the marketplace today. We as practitioners don't have to come up with these designs, but we need to know what to use and when to use it. And that's the key. Let's review one factor at a time, the good, bad, and the bad about OFAT. The good news is it's simple, it's intuitive, it's the way we're originally taught. I remember in my first chemistry class in high school, the teacher says, well, if you want to know, we're testing time and temperature and pressure, mainly temperature and pressure, I guess, and their effect on some sort of response variable, which was a yield of a chemical reaction. And I remember the teacher saying, well, if you want to know the effect of temperature on the yield of the experiment, you need to hold everything else constant and just change temperature. And then you find the optimal temperature, and then you hold that constant, and then you change pressure in holding everything else constant, and you'll find the optimal pressure. Well, that's the way we were taught, unfortunately, sometimes incorrectly. It is a very simple approach, one factor at a time approach. It's intuitive. You say, well, if we want to know the effect of this factor, we should hold everything else constant and just change that factor. Well, if we're doing that, we're probably wasting a lot of time and a lot of money in our testing approach. And almost all organizations test, whether they realize it or not. Testing is done by almost every organization in the world. The bad news about OFAT, it's a waste of resources, as I said, time and money. You will not be able to estimate variable interaction effects, and the combination effects are really what are serious out there. If we have a problem, it's usually not just one factor. It's usually a combination of factors that is creating issues. And we won't be able to, with OFAT, be able to generate prediction models and thus not be able to optimize performance. So there is good news about OFAT. There are OFAT practitioners out there in the marketplace today. Physicians typically are very adept at one factor at a time testing. They will change one factor at a time to see what impact it has on the physical response. And they are fairly decent practitioners of that. But generally speaking, they will not be able to optimize performance, and they won't be able to evaluate interaction effects as well. The oracle or the best guess approach would be something like this. Let's go back to the performance tuning, and let's take 5 factors, A, B, C, D, and E, which I'll be short for CPU type, CPU speed, etc. Notice in parens I have the same 2 levels that we had before. So this is a 2-level design, and in the design matrix that you see below, and this is the first time I've shown you a design matrix, this matrix shows you the test combination or the runs that we would test. And say we have expert number 1, which will correspond to run number 1, or the first row in this matrix. This expert believes that the best combination for maximizing the number of home page loads per second is shown as depicted in run number 1. That is, A is the first setting, B is the second setting, C, D, and E are all at the first settings. And you can go back to the parentheses to see what those settings are. So A being 1 refers to an Itanium CPU. B being 2 refers to a 2.5 gigahertz CPU speed, and RAM, hard drive, and virtual memory are all at the first settings as depicted in parens, the levels there. So those are somewhat called, sometimes called coded settings for the variables. It's easy then to see the design matrix and the patterns that are involved in that design matrix. So if we had 8 different experts in the room, and each of the 8 experts had their preconceived and experiential background that would say this combination will be the best combination to enhance the Y value, and Y in this case bigger is better. Now they did these 8 test cases, and those were the 8 results that they got shown in the Y column. Let me ask you a question. Each of the viewers should be able to answer this. Does factor D, take a look at the column labeled D. D happens to be hard drive size. Does factor D shift the average of Y? And at first glance, your answer will be probably, well, maybe, because when D is set at the 1 setting, or at the low setting, 50 gigabytes, we're getting smaller, number of home page loads per second. And when D is set high at the 2 setting, we're getting larger ones, because the column labeled D is certainly correlated with the column labeled Y. But if you look more closely at the design matrix, look at column C. C and D are perfectly correlated. In other words, C and D are in DOE language aliased or perfectly confounded. And so it is very difficult to tell how much of that change in Y is coming from C, how much of it is coming from D, because C and D are aliased. And you know what an alias is. An alias is, alias names are two different names for the same thing. Now the same thing here is the 1, 1, 1, 1, 2, 2, 2, 2 combination as you look vertically in the column C and D. So we have two different names associated with that kind of pattern. And if you look at column E, it's not perfectly confounded or aliased with D or C, but it's heavily confounded or partially confounded, because for the 4 1s of D, you have 3 1s and 1 2 for E. And for the 4 2s of D, you have 3 2s and 1 1 for E. That is not balanced. That balance is going to hurt us when it comes time to evaluate the result of the test. Now, columns A and B are nice, and this is why this is a makeshift example, so I can show you in the same design matrix the difference between confounding, aliasing, and where we have perfect balance as shown in columns A and B. We have perfect vertical balance throughout all of the 5 columns because you have 4 1s and 4 2s in each column. But if you look more closely at columns A and B, we also have horizontal balance, not only vertical balance, but horizontal balance. For the 4 1s that you see in column A, and let's see if I can get my mouse on there, for 2 of the 1s you have a 1 setting, and for 2 of the 1s you have a 2 setting. So B is broken up evenly for the 4 1s of A. Half the time B is a 1 setting, like there and down here, and for the other 2 settings for 1, B is a 2 setting. And likewise for the 4 settings of A being a 2. Half the time in the B column you will see a 1 associated with that, and half the time you will see a 2. So A and B are said to be orthogonal, or balanced vertically and horizontally. And that's what we'd like to see throughout the entire design, not just in column A and B, but we'd like to see that throughout all of the factors in our design. So what we really have from a Venn diagram point of view, what we have in the previous design, if you look at the big circle in the upper left, that the big circle represents the total variation in Y, and the circle labeled C equals D, that's the portion that would be explaining some of the differences in the Y's, but we cannot tell how much of that circle is C and how much of it is D. The aliasing pattern is creating this type of situation. So it won't allow us to determine how much of that circle is C and how much is D. Making matters even worse, E is partially correlated with C and D. So the cross-haired area, we can't tell how much of that area is really coming from C, how much of it's coming from D, and how much of it's coming from E. What we really want is the Venn diagram shown in the lower right, or the rightmost side of your page. We want a design that when we are done collecting the data in the test, we can then evaluate each of the factors independently. C, D, and E. We now know exactly what C is providing, what D's impact is, and what E's impact is. Now, how do we obtain this independent evaluation of effects? It's through these orthogonal or nearly orthogonal designs, which I classify as statistically designed experiments or design of experiments, which is kind of an interesting term in itself. But DOE distinguishes itself from all of the other combinatorial testing techniques by having orthogonal or nearly orthogonal designs. Now, this is not the only discriminating property of DOEs. There are other things. There are other foundations like replication and randomization and things like that that go along with DOE. But the ability to evaluate effects independently is very, very critical, because independent evaluation will allow for you to get to cause and effect relationships. Now, there are a variety of designs shown there, from full and fractional factorials through Plackett-Berman, Latin squares, Hadamard matrices, which can be put together in a class of designs called Taguchi designs. There's box-Benko and central composite designs, which are also known as response surface designs. There's a new type of design out there today, nearly orthogonal Latin hypercube designs, an algorithm of which was generated by Tom Schock at the Naval Postgraduate School, which is used in many software packages today to generate designs which are good for screening many factors at lots of levels. And typically we see NOLHDs being used in simulation types of experiments when you have large-scale simulation and you want to generate an emulator or a low-fidelity model. The nearly orthogonal and hypercube designs come in handy. But anyway, those are just a few of the orthogonal or nearly orthogonal designs that are out there today. But I don't want you to get bent out of shape over this thing called orthogonality, because all it means is balance. And I'm going to show and demonstrate a two-level orthogonal design for 3 factors each at 2 levels. And I want you to just think logically about this. We have 3 factors we're going to test. These are typical out there in industry today: time, temperature, pressure. And look at the actual settings. Now, if we were going to do a full factorial, that means every possible combination. So we have 2 choices for time, 2 choices for temperature, 2 choices for pressure. You see those in parentheses right above A, B, and C in the actual setting matrix. Now, we're going to actually fill in this matrix from a very practical, concept point of view. Obviously, if we're going to fill in column A first, we've got to fill in column A with 5s and 10s. Now, would it be okay for me to put 6 5s and 2 10s in the 8 slots in column A? Absolutely not. It would not be a good thing because we lack balance. And I think any tester would understand that. So I'm going to show you what the software package we use does. It puts the 4 5s in the first 4 slots and the 4 10s in the last 4 slots. It doesn't matter where those 4 5s and 4 10s go, but you got to have 4 of each. But the way we're putting them in now, you will see the pattern, and the software does this automatically. Now in the temperature column, we've got to put 4 70s and 4 90s in there somewhere. Would it be shabby of me to put the 4 70s in the first 4 slots, the first 4 runs? Absolutely. Because we'd have in the 4 90s in the last 4 slots? Absolutely, it would be bad of me. Why? Because I'd have the same situation we had with C and D in the web performance example. So we're going to split up the 70s. 2 of them are going to go with the 5s, and 2 of them are going to go with the 10s. And we're going to split up the 90s. The 4 90s, 2 of them are going to go with the 5s, and 2 of them are going to go with the 10s. And if you go to the pressure column, you can see what comes next. We alternate them one at a time. And right then and there, you have a fully balanced design. Okay? And the bottom line is that is what you would run in a full factorial design for 3 factors at 2 levels. In fact, this is probably the design that I've seen used most often out there in industry. It's a very simple design. It's effective, it's efficient, and you will see in a second other effects that you can also get independently from a design like this. Now, when we go to the software, we usually let the software code the data. By code the data, we do this because the 3 factors have different units of measure attached to them. They have different magnitudes of numbers. Notice pressure is in the 100 to 200. I suspect that's PSI. Time is in the 5 to 10 range. Now, when we analyze the data by way of regression or whatever, the coefficients, the impact that the factors have, will be dependent upon the magnitude of the number that is involved in the unit of measure for each of those factors. Now, we want to put everything on the same playing field, and the way we do that, or the software does this automatically, you just have to tell it what your low and high setting is. The software will code the settings. And I just want to show you the difference between coding and the actual settings. Because when interactions come into play, when we look at a time-temperature interaction, an A-B interaction, which would be designated by column A times column B, you can see what we would get if you would take the column A times column B under the actual settings. You'd get a 5 times a 70 or a 350, then you'd have a 5 times a 90, a 450, and so forth. But if you do that in the coded matrix, here is what the difference will be. On the next slide, I'm going to show you if you were to take all the interaction effects of those first 3 columns A, B, C, the uncoded is shown on top and the coded is shown on the bottom. Well, if you were to take those 7 columns and put those 7 columns into any stats package and look at the correlation, you will see unbelievable correlation in the top matrix. because you can see as you take A times B, AB is going to get bigger as A gets bigger and as B gets bigger. So that is, from an evaluation and an analysis point of view, that's going to create a little bit of havoc. But if you do it on the coded format, if you took column A times column B, like down here, these guys, these two columns, you multiply them to get column AB, guess what? Column AB will be completely uncorrelated with column A and column B, which is not the case up here. Column AB will be hugely correlated with A and B. But this down here is what we want. We want all of the effects that we might want to evaluate to be evaluated independently from all of the other factors and effects. So down here, when you take the coded values of A and B and C and you start multiplying them together, item by item, that is row by row, you will get a new matrix that has completely uncorrelated columns. Notice that the ABAC, BC, and ABC columns, they all have 4 1s, they all have 4 minuses in there. And each column, all 7 columns, have their own independent, uncorrelated profile. And that is a good scenario we want for analyzing and evaluating the results. Let me just go to the next. The beauty of orthogonality, when we start multiplying these factors together, I'm going to blow this up a little bit. I'm going to dispense with 1. A minus really means a -1. A plus really means a +1. But you get the idea here. Those are the 3 columns. But anytime you're testing 3 factors, you will have a interaction effect between A and B. So when you multiply column A times column B, you'll get the column labeled AB, which has its own unique profile, has 4 pluses, 4 minuses, as we showed in the previous page. If you take column A times column C, AC will have its own unique column that is different from the previous 4 and completely uncorrelated with each of the other 4. Likewise, for BC, when you take column B times column C, you'll get this orthogonal column called BC. And, of course, there's a 3-way interaction called ABC. And the point being is you have this vertical and horizontal balance throughout the design. So for you mathematics engineering folks out there listening today, here's the definition of horizontal and vertical balance. If you consider each of these columns, 7 columns, call it a vector. Each one of these vectors is different. You have 7 vectors. If you took the dot product of any 2 vectors or any 2 columns, you will get 0. In other words, if you multiplied any of the 2 columns together and added up the resulting 8 multiplications, you will always get 0. That's what orthogonality is. Now, it's not so important you know what orthogonality is, because in the DOE literature, we have all of these DOEs are going to be orthogonal or nearly orthogonal. And what it buys us is the independence of evaluation. And that's what's critical. It's what it buys us as an organization. That is independent evaluation. And what does independent evaluation give us? The ability to get to cause and effect. It is very difficult to get to cause and effect if you don't have the ability to evaluate independently. So orthogonality is probably the #1 principle that is unique to DOEs, that DOEs have, that other designs like OFATs and the Oracle best practice or the best guess approach do not have. So if you were to ask me what my elevator speech is for design of experiments, it's an optimal data collection methodology, and in testing we are collecting data. It's the most effective and efficient way to collect data in a scenario where you're trying to find relationships between outputs, that is performance, and the factors or the inputs that can affect and their interactions that can affect the performance. What DOE really does is interrogate the process. We ask the process questions, and those test cases are the questions. They form the question format of interrogating a process. We can use DOE to identify those relationships that are important. We can identify important interactions between process variables. We can use it to optimize a process, to assess risk. We basically use DOE to change I think to I know, and basically DOE is the science of test and evaluation. It's the connecting point between test and evaluation. And so DOE will help us determine how the inputs affect outputs in a variety of ways, the mean and the standard deviation. In the first scenario there, factor A, let's say factor A is altitude, and we change the altitude purposely, systematically in a DOE, and we see what impact it has on Y, like maybe the distance to detection or whatever y is. If A is changed, and that is the impact that A has on y, we say that A affects the average. Now, the average is the balance point of a distribution. We're showing two different normal distributions here, and these distributions don't have to be normal, but the normal is a nice one because it's the most common one out there, and the shape of the distribution is shown in factor B's effect is the standard deviation. The standard deviation is the shape parameter of a normal distribution, where the location parameter, the center, is the mean. So you can see factor A affects the center of the distribution, shifting the center. Factor B shifts the standard deviation or the shape of the distribution, but not the center. And factor C does both. Factor C affects both the mean and the standard deviation of the output. Factor D has no effect. And sometimes you say, gosh, what a bust that was. Factor D has no effect. Well, if factor D is two different sensors or two different vendors, factor D may have no effect, and that may be a way that we can save some cost. But at any rate, DOE helps us determine these effects on the mean and the standard deviation of our performance measures, and we cannot do that. We cannot make these conclusions unless we can evaluate these factors independently. So that's the key. I'm going to speed up here a little bit. DOE, those are some of the basic underlying principles. DOE can be used to screen, model, and perform verification and validation or confirmation testing. Those are the three primary reasons we use DOE. Screening is separating out the critical few from the trivial many factors. We've got to find out which of the factors are important, which ones are not. Modeling allows us to actually build a mathematical relationship, a mathematical model, or a function. Sometimes we call these transfer functions. We need these functions in order for prediction, assessing risk, and optimizing performance, or finding where our performance is maybe not so good. And to be able to do this, we have to be able to evaluate interaction and higher order effects. Sometimes we don't want to model. Sometimes we don't want to screen. Sometimes we just want to confirm that the system is performing in accordance with its specifications and requirements. If this is the case, we can use DOEs for this as well. So screening, like I said, is separating out the critical factors from the trivial many. We go back to our Sonar system test, the active Sonar system. We had those 8 factors, 8 input arrows and 1 output. A good design to use for screening here would be an L18 design. This 18-run design is a little bit different than the design I showed you before, the 8-run design that had only minuses and pluses. You'll see in this design, for columns 2 through 8, you have 3 levels. So this is a 3-level design for factors in columns 2 and 8 that we would assign to columns 2 and 8. And factor 1, or the first column, is reserved for a 2-level factor. This is a very commonly used design out there, and that would be an appropriate design to use for this scenario. The modeling designs, as I said, build functions or mathematical models. This is where we want to get y equals f of x or s hat. S hat and y hat are the two functions that we degenerate. Y hat for the mean of the output distribution, s hat for the standard deviation of the output distribution. And so where do we get transfer functions from? Well, sometimes if you're an engineer, you know what those relationships are. Like for the impedance of a 9-volt circuit with 2 resistors, you know, the equation there, if you're at EE, you probably know that without going even to the literature to find it. I would not know that. If you're a mechanical engineer, you probably know what the equation for magnetic force at a distance x from a center of a solenoid is. I don't know that. I would have to look that up. But chances are in a test environment, we don't know that. So the best way to get that is to get approximations through DOE, historical data analysis, and simulation. And or some combination of those. But DOE is the way that we have found gives us the best way to get these transfer functions. Now, here's an example of a transfer function on 5 variables or factors that my friend Bert Sillich, formerly a colleague of mine at the Air Force Academy, came up with years ago. He had 6 aeronautical characteristics. Now, this guy's a medical doctor, but he formerly was, well, he's still an aeronautical engineer. But he came up with a design to test 5 different factors on a 3-wing fighter aircraft to generate 6 aeronautical characteristics. Now, if he had used, and the full factorial design or total or all possible combinations here, you have 3 choices for each of 5 input factors, 3, 3, 3, 3, and 3. 3 to the 5th power if you were to do a full factorial design, 243 test combinations. Well, we're never going to be able to afford that. So Bert did a central composite design, which is actually 30 test points that gives him almost everything from an evaluation and analysis point of view that the full factorial would give. So it's a really good trade-off design, and Bert generated these 6 equations. These are models or transfer functions for coefficient of lift, coefficient of drag. Those are his 6 aircraft equations that he generated. And you say, well, Mark, we don't have any 3-wing fighter aircrafts in our inventory, DoD inventory today. Well, we may not have that, but we certainly have UAVs that are quite prominent in the news today that have the tail assembly is constructed of 3 types of things, and these equations have been used by some vendors to optimize the performance of the tail assemblies of these UAVs. So it has been used in the literature. Bert owns the patent to that, and he's the guy that came up with the transfer functions or the equations. So those are examples of models. Other models can be, in the medical industry, it's very, very important to be able to fuse titanium and Cobalt-Chrome for an artificial knee joint. Ray Chowdhury was able to build a model with interaction effects that would be able to do that. Titanium is very friendly to bone, but it's not a good joint structure or joint composite. You need a Cobalt-Chrome to do the joint structure, the part that forms the joint. Basically, the shiny stuff here is the Cobalt-Chrome, and the stuff that goes into the bone is the titanium. Now, you can thank Ray Chowdhury for finding interaction effects by way of modeling to solve this problem and get the artificial knee joint on the market quicker than we would have without DOE. DOE can also enable us to do critical parameter management, which is a systems engineering best practice that is extremely useful for technical product performance evaluation and prediction. It's useful in decomposing critical operational issues and developing linkages between measures and system attributes and capabilities. As you can imagine, in a simple IPO diagram, the output of one IPO could be the input of another IPO, and that's what I mean by this cascading of IPO diagrams here, where at the top level, when we say the system can do this, we can then drill down to find where our highest risk areas are, which are the X's at the lowest level that are going to possibly create problems or give us the best problems. So the Y's that are outputs of one process could be inputs to another, and this whole idea of critical parameter management is enhanced. You will not be able to do this without DOE, I can guarantee you. A critical operational issue is just usually set aside by phrasing it as a question, like, will the system detect the threat in a combat environment at adequate range to allow for successful engagement? Well, just in that question, there are words that just speak out at us, like detect and engage. Those are performance measures. Threat, you have different types of threat. You have different types of ranges. You have different types of combat environments. And you can see that detection could be a function of a variety of X's, and then engagement a function of not only detection, but a bunch of other factors as well. So in the COI business, critical operational issue business, and CPM, this is how the connectivity can be ascertained, is through design of experiments. Google is one of our customers who just does all kinds of DOEs. Now, they've got data coming out of their ears, so they typically do full factorial designs because they have lots of data. But when they do DOEs, and they do lots of them, they have so many people wanting to test that when we submit a query, they automatically think of an opportunity to test something. And so from Daryl Pregibon from Google, he says, we evangelize experimentation or testing to the extent that we provide a mechanism for their advertisers to run their own experiments. Of course, Google likes to do what? They want to maximize the number of clicks because that has some financial impact for them. So Google is a very strong proponent of DOE. They use it all the time. Typically, they use a lot of full factorials, but I think we're showing them they can be more efficient and effective with some designs other than that. Verification and validation is the last thing I want to talk about today. And I want to talk about this thing called high throughput testing, which allows you to do confirmation testing and verification validation testing and also do mixed factor, mixed level testing if you have to screen. It's not a good modeling design, but you can possibly screen with it simply because we do have orthogonal or nearly orthogonal designs right now in software that will do that. So even though this is an outgrowth of the pharmaceutical business or combinatorial chemistry, we use it now heavily in software testing, materials discovery, integration, interoperability testing, functionality testing, system of systems testing. I think you can see this best by taking an example. Here's a simple submarine threat detection example where we have, I guess we have 7 factors there, and in parentheses you see the number of levels. The number, or V levels, the number of levels are shown in the rightmost column. And if you were to compare an all pairs or a type of high throughput testing with a full factorial, if you multiplied all those levels together, 3 times 3 times 2, so forth, you get 1,296 possible combinations. Well, there's just no way we're going to be able to test that many cases. So can you get good test coverage in a verification, validation, or confirmation testing with a significantly reduced number of test cases? And the answer is yes. If you look at all pairs testing, that is, if you take any 2 of those factors and you want to test all possible pair combination or two-way combinations, you can do that with these 15 test cases. Now, these 15 test cases were generated by RD Expert from FATKey Corporation, and these 15 test cases actually provide you a nearly orthogonal design for main effects. So you can evaluate those seven factors, submarine type, ocean depth, sonar type, target depth, and so forth, all independently with this design. Now, if you wanted the full orthogonality, perfect orthogonality, it will cost us 18 test cases. So 3 more test cases gets you perfect orthogonality, but in my experience, a nearly orthogonal design, such as this one, meeting our criteria of orthogonality or nearly orthogonal designs would be sufficient. Now, let me just go through this. Let's suppose you tested all 15 of these test cases, and the outcome was either good or bad. It was binary. In other words, the first 14, I'm going to choose row 15 simply because it's the last row and it's probably the easiest row in this matrix to see. And I want to show you what we're doing, what combinatorial testing in this case does. You have 7 factors or 7 columns here. How many two-way or pair combinations do we have in each test case or test run? You have 7 times 6 divided by 2 times 1. That's how you take 7 things taken 2 at a time. There are 21 possible two-way combinations. Now, we're going to just take the quick time and go through all 21 of them here in row 15 to see. Let's say 15 is the only one that did not perform well. Everything else worked properly. Which two-way combination could be causing the problem? So if you look at S3 and shallow, we'll take S3 with shallow. That's been tested before. You can see that right up here. S3 and shallow was tested before in run 7. We didn't have a problem there. How about S3 and passive? You find S3 and passive before. How about S3 and deep? S3 and deep is done right up here somewhere. S3 and deep is somewhere. I thought I saw it right here, run number 7. And you can go through S3 and sand. It is done before. S3 and autonomous is done. S3 and minimal is done. Shallow and start with the second one and now go forward. Shallow and passive is done. But you get to sand and minimal. The sand and minimal is not been done. You will not find that anywhere else in the previous 14 runs. Autonomous and minimal, you will. That's right up here. But of those 21 two-way interactions, the only two-way combination that had not been tested in the previous 14 runs is sand and minimal. And now I don't know the underlying algorithm that is used in RD Expert, but I suspect run number 15 had to be added on there to get the sand minimal combination that has not been tested before. But here's this concept of high throughput testing. Every run is testing 21 different two-way combinations. And of course you have some overlap. You're testing some of these more than once, but the sand and the minimal is tested only once, and that is in combination, test combination 15. So this gives you a little bit of feel for what the software does. You don't want to do this by hands, my friends. By hand, this gets too complicated. You've got to have the ability for the software to do this. Here's one for 15 factors each at a number of levels. It's a command and control test example. And you can see the variables or factors and the levels that are being tested. If you multiply all of these levels together, you will get more than 20 million combinations. So clearly, you cannot test that many. But if I used RD Expert to put these 15 factors in there, each at the number of levels you see there, it will generate a 35-run nearly orthogonal design, 35 test cases in place of 20 million. Now, if you wanted the pure orthogonality, this is a nearly orthogonal design, 35 test cases. It'll take about 64 test cases. The result is not of my saying that is not shown here, but it would take about 64 test cases to get pure orthogonality, but we can do it in 35 test cases with this nearly orthogonal design. So I'm just showing you getting good test coverage. You are getting all pairs. You are guaranteed in this 35-run design to get all pairs or all two-way combinations tested. Now, will you be able to build a model? Probably not, but you will be able to evaluate those 15 factors at where you have the highest risk and the lowest risk. And let me show you that with a final example I'm going to show you on electronic warfare. There are 6 factors here, 5 of which have 3 levels: frequency, PR type, PRI type, scan type, peak power, and illumination. All have 3 levels. You see what the levels are over here. And frequency diversity has 2 levels. Now, the design that the RD Expert will point out and that our software would point out also is an 18-run design. This turns out to be the infamous L18 that I showed you before. It will test these 6 factors, getting independent evaluation. Now, when you do these 6, now I'm showing you some output here too, thanks to Kedar Fatke. I'm showing you some output that he gave me from this particular test. Now, these are the number of errors. This is not a binary output. These are actually recorded errors on each of these 18 test cases that were committed during these test runs. And so bigger numbers are worse, smaller numbers are better on the Y response variable. So let me show you what you can do when you have an orthogonal design like this. Even a marginal means plot like this will tell you a whole lot about the effect of these 6 factors. Remember, smaller data points are better because we're measuring number of errors. So the error rate is on the vertical axis, and you can see which factors stand out. Factor B, factor C, not factor D, but factor E and factor F. You can see that. And if you want to look at the highest risk areas, they are these particular areas of your operational environment. That's where you're going to have the highest risk area. So lowest risk is going to be down in this area. But of course, high risk will equate to the low setting of this factor. This is factor B. That's the second factor. The highest point occurs at the -1 or the low setting. The highest points on the other 3 significant factors are occurring at the high level. So it's always the +1 or the high level setting. And so the high frequency with agile PRI type, low peak power, and 100% illumination is going to be your most critical and the most risky part of this particular design or this particular operational environment tested by this particular design right here. So you can do a lot of simple analysis just by looking at the graphical results. But let me remind each of the viewers here today that we cannot do that unless we can evaluate these effects independently. We cannot make this conclusion unless the effects are capable of being evaluated independently. And so that is a key outcome. The HTT or the all pairs testing, HTT involves all pairs. In some software packages, you want to test all 3 ways, all 4 ways, all 5 ways. We found that all pairs testing gives you very, very good coverage at a very minimal or limited number of test cases. And so you need software to generate these designs to get complete coverage and get very good coverage here. But you can use this for a variety of applications. At John Deere, we use it for pre-testing or pre-screening large DOEs that are run on simulators to ensure that all 2-way combinations are feasible before you go into a big experiment, on a computer simulator, for example, that you're doing, 300 test cases or something, and each test case takes 20 minutes on the computer. So we want to make sure that we get all 2-way combinations are feasible. We can also generate outer arrays of noise combinations using these designs when we do other types of DOE. So high throughput testing is very, very powerful. Now, if you're wondering how you embed this culturally, how you embed DOE, and that's what I call operationalizing, it really means making DOE operational in an organization. Well, we recently wrote a book of 50 best practices, but the top 5 are these right here. Number 1, you got to have coaching on projects as an absolute must until your practitioners can come up to speed and become competent in all of the DOE. So coaching is essential. We also need to generate a culture of DOE, a keep it simple statistically approach, a KISS approach with easy to comprehend materials, easy to use software. You need something that every engineer, that every practitioner in the organization can use to use the DOEs. And we need to be able to generate and propagate quick-hitting successes using DOE. We need to have leadership on board. They don't need to know all the details and the designs, but they've got to know what DOE buys them in their own organization. It's a phenomenal test technique. It's the best test and evaluation technique out there today. And you know, I'd like to see an organization that doesn't test something. Everybody tests. And if you want to be on board with the best testing techniques, this A/B testing that you see out in the marketplace, that's nothing but one factor at a time testing. So leadership has to know that. They have to buy in. They have to be reinvigorated. Our leadership changes in most organizations so quickly that we have to continuously educate the leadership on this. And then a metric we use in our clients to look at if the culture is being impacted by DOE, and that is, do we have transfer functions for the critical to customer or the critical performance measures? That is validated transfer functions. And because if we have those, we can optimize, we can predict, and we can assess risk. And that's that modeling portion of the DOE that I talked about before. The 3 reasons for screening, modeling, and verification and validation testing. So in summary, I just want to summarize the key takeaways that I'm hoping that you took away, and these will probably help answer the question, well, what's so great about DOE anyway? Well, as the background of this presentation, I told you different approaches to combinatorial tests to include OFAT, Oracle Best Guess. DOE brings the orthogonal or nearly orthogonal designs into play, and it can be used to screen, to model, or perform validation testing. What is DOE bias? Well, this orthogonal designs, they are key to evaluating the effects of factors and their interactions independently from one another. Orthogonal designs also allow the use of power and significance when planning for the appropriate sample size. I have not addressed power and significance in this short presentation, which I just don't have time to do. But these designs allow us to do that in a much more straightforward fashion than if you had some other type of design that is not DOE oriented. DOE, in my estimation, is the key link between test and evaluation, because most practitioners probably don't understand to the extent how you test, that is, how you collect the data, will have an important and a magnitude, order of magnitude influence on how you are able to evaluate or analyze the results. So DOE is the linkage between test and evaluation. It really is. And factorial designs, they're great, but in a world of large, complex test design spaces, we're going to need something else. And that's where this all pairs testing or a type of high throughput testing can help us get great test coverage with a minimal number of test runs for a test scenario involving many factors or mixed levels of factors, as we demonstrated with some of the examples here at the end of this presentation. So this is a very useful design strategy for testing when we're trying to verify, validate performance in an operational envelope. And these designs, because we have the software today, can be orthogonal or nearly orthogonal, which buys us also that ability to evaluate the effects independently at their different levels. So that's what I hope you take away from this. I just want to finish by saying learning about DOE and making it an operational in an organization does not have to be difficult. If you follow the 5 best practices for deploying DOE, it can happen. It does not have to be made hard. It does not have to be reserved for statistical gurus who have to have PhDs in stats to do this. We have high school practitioners at various companies who are very good practitioners at DOEs, and they get phenomenal results, increasing their knowledge at very, very low cost.